Welcome, everyone. Today, we are going to explore a rather simple sounding but surprisingly radical idea, which is instead of first turning observations into a conventional analysis and then running a forecast model on that, can we learn to forecast directly from what the observing system actually measures? I am joined today by Eulalie, who has been working on graph DOP and related developments at ECMWF, and Azadeh, who leads the development of Ocelot at NOAA. I would try to keep this informal. Maybe sometimes I will ask simple, stupid questions because I want to understand not only how the system works, but also why particular decisions were made. So welcome to you both on this podcast. Before we get into all kind of details on architectures or acronyms, I would like to ask a bit more personal side of the story, that what first attracted each of you to direct your attention to this direct observation-based prediction? Because our field is so vast, you can choose your problem, and then, but why this one? Why are you working on this problem?
Okay, I go
Yeah.
first.
Okay.
What first attracted me was the gap between how much information exists in the global observing system and the fact that many leading machine learning weather models don't learn from those measurements directly. They are usually trained on analysis or reanalysis, which are incredibly valuable, but are already the output of a complex data assimilation and numerical weather prediction pipeline. But then GraphDope was an inspiration for us. It provided a compelling early demonstration that an end-to-end model could learn directly from observations and use those observations to predict the future observations.
Mhm.
When we learned about that work, we became interested in exploring the same broad scientific question through Ocelot. The question that interested us was whether we could learn atmospheric evolution directly from heterogeneous observations while preserving their native timing, sampling, and geometry. And also, some measurements are difficult to exploit fully in existing systems. So, Ocelot allows us to investigate whether machine learning can learn useful relationships across instruments directly from the observing system.
Cool. Thanks. Eulalie, what would you like to say?
Yeah, just for a bit of context, I joined DCMWF just at the beginning of the GraphDoc project. So when I first applied to the job, it was listed as learning from observations, but there was no, I think, no idea and no project that had started yet. It was just, just the idea that was blossoming within the DCMWF. But as Azadeh said, I was working with observations beforehand in remote sensing, and it's true that there is a huge information content in these observations that we can exploit. And of course, for DVAR or different assimilation systems already do that and do that very well, making these analysis or reanalysis data sets. But if you look at models like machine learning forecasting models nowadays, they are all trained on these analysis and reanalysis data sets, and they have now a similar kind of skills set. And if we want to go maybe beyond that, yeah, it's interesting to see if we can go beyond that using all the raw observations directly. So I think that's something that really attracted me into working in this field.
Cool. So we can slowly start building into this momentum. And in that line, I was thinking, what would be the most basic version of this whole work pipeline? So for example, let's imagine at 00 UTC, we get the observations arriving from satellites, radiosondes, aircrafts, and all kinds of different observation systems that are there from space and from ground. Maybe you could take us through the journey from those measurements into the forecast that we get in GraphTop or Ocelot. How does the pipeline looks like?
Maybe I can start. So in GraphTop, for as you say, for instance, for a 00 UTC forecast, we would take all the observations that fall within the assimilation window used for a 00 UTC forecast. So generally with GraphTop, we use observations that would go from 9 p.m. to 9 a.m. This corresponds to the long window data assimilation window at ECMWF. So we would kind of take all these observations, we then process them into machine learning friendly formats. So we use ZARs, we apply there some quality control, some range checks, etc. And once we have our kind of set of observations for 00 UTC, then these observations can be fed to the model as such. And then the model will output a 10-day forecast for all of these observations in their raw format. So if we're giving it some satellite observations, it will also forecast some satellite brightness temperatures. And we have a special treatment for everything which is in situ or conventional observations, so radiosondes, aircraft, surface stations, etc., that measure actual physical quantities. For those, we not only output a forecast at their locations, but we also output a forecast on a grid, which we can then post-process and verify, etc., as you would with a general forecasting model.
Okay, I have some questions, but maybe we can continue with Azadeh on Ocelot. Is there something new that you do or something different?
It is almost the same. I think Eulalie explained the whole picture.
Okay.
Almost the same. Yeah.
Mm-hmm.
Do you want me to explain? I think it's just repeating.
Yeah, it's fine. It's fine. It's fine. But then automatically the question that comes to my mind is based on the last explanation of Eulalie of this conventional ops. So on a location, you have that observation, that value, and then you can predict on that same grid point. But then you also say that it is not only at that location, but also to all the grid points. Without going too much into technicality, can you say how is it done? I mean,
in very easy terms, during the training, the model will learn kind of relationships between, for instance, satellite observations, which are global, and these very sparse conventional observations that lie at certain, certain grid points or certain locations. And then once the model is trained, we can apply these same correlations to give a forecast basically anywhere. So it can apply the correlation as it has learned during training, and will just output a forecast at a given grid point, knowing the orography, knowing the lat plan of that grid point, etc.
So just to get the complete picture, your input could be arbitrary grid points as well as satellite orbs from the globe, but then the output is a gridded format, like a proper all the grids.
In the case of GraphTop, it's both. So we have sparse radiosondes coming in. We also have sparse radiosondes coming out, which are then used in the rollout of the data of the model. But alongside that, we also output a gridded version of the radiosondes or a gridded version of the surface stations, which gives us the actual forecast in which we're interested or users are interested in.
Thanks. Azadeh, would you like to add, or is there something new or different in Ocelot?
In Ocelot, during training, we only forecast in observation space, and during inference, we have forecast on fixed grid.
Okay. So let's say there, like if the satellite measures brightness temperature, but that is per se not a physical quantity that we are interested in. For example, I don't know, cloud top height or surface 2-meter temperature. So, these are two different worlds. One is the satellite observation world, and the other world is more that we are used to seeing, which comes from the model version, like numerical models. So how do you connect them? So you continue your, input from the observation space, you get your forecasting in that observation space, I would still say. But then the variables or the state space in which you are interested in is more, it's more conventional from the numerical modeling side. How do you convert it? Or is it not that tricky? Or this is a stupid question that I'm asking, I don't know.
the physical quantities that you're like 2 meter temperature, etc., they come also from observations, just a different type of observations. So they are coming from the radiosondes that measure temperature at 850 hectopascals, or surface stations which are measuring 2 meter temperature where at the station location, etc. In our case, we don't use any level 2 data, for instance, which would go from the satellite observations to these quantities. We could also imagine a model where you train on level 2 products, and that would make things possibly easier. But in our case, we only use observations. So the model then is responsible for making the link between the satellite observations and the other observations that measure in model space, as you say. But it's in fact still observation space. It's just different kinds of observations.
Is it the same in Ocelot? Is it? Okay, cool. So maybe we can now slowly move to the scientific motivation of our discussion. When did the first paper of GraphTop came out, or when did the work started in this direction in ECMWF?
And so I think it started early 2024, and we had a first paper in summer 2024, but not really on GraphTop. It was more on the concept AI DOP, so direct observation prediction, but without a clear model. There was no clear model yet. And then the first GraphTop paper came out in December 2024.
Okay. And when did the activities started in NOAA? Was it there?
Early 2025.
Okay. So I understand this point that data assimilation is still very computationally expensive, but just for the overall wider audience, it would be good to have this understanding that, okay, we know that classical data assimilation exists, and NWP, all the different components in there have been refined for decades. And well, they work good, or I would say remarkably well, given the medium range. Then what was the strongest reason for building a completely different route from observation to forecast?
The motivation is not to replace data assimilation. As you said, yeah, DA and WP work remarkably well. The scientific opportunity is to ask whether we can learn atmospheric evolution directly from observations without making a graded analysis, the required middle step. Some parts of observing system are in the current system are still difficult to use fully. For example, cloud-affected radiances, surface-sensitive channels, observation with complicated errors or representativeness issues. So an observation-based model like Ocelot, GraphTop may be able to learn useful relationships across those different measurements directly. But on the other side, it will create a stronger dependence on the observing system itself. Calibration changes, missing satellites, regional data gaps, QC changes, and systematic biases can all influence the model. So those issues don't disappear. They become part of the machine learning problem.
So you let the machine learning model decide? Because I guess, because what I understood is that there is also a data control or data quality check part there, which is actually, I would say, it's a knowledge heritage that without that, the model could learn completely something different. And then, so what we feed in, if that is, not quality control, or if it is per se, I would not call it garbage, but if it is not quality control, you cannot expect the model to do a magic.
That's totally correct. Yeah. Because of that, the processing is very important part of our work because we are using observation as a target, and it is a supervised learning. So yes, it is a very important part of our work, the pre-processing of the observation. Mm-hmm. Right now, we are using the knowledge I have from the current data assimilation systems, and we are using observations that we are familiar. We are using the current QCs and spinning core satellites, but maybe in future, when we have a new satellite observation, we need to come up with a new plan for that.
Maybe in that same line, I was wondering that, so if you think about the global observing system, we have a vast pool of different kind of measurements which the satellites take. which family is difficult to include it in the current, let's say, end-to-end observation-based forecasting? Or are you managing everything? So for example, it could be like infrared radiances, it could be like visible channels, it could be the channels which are more sensitive to the surface. So, when you decide whether this particular, I don't know, part of the wavelength will be part of my, like the training, do you see that, okay, in this region, I don't know whether this observation could be trusted and should be part of the training? How does this decision goes?
So I think as Ade said, we at ECMWS as well, we exploit our knowledge on observations and how they affect classical data assimilation.
Okay.
So a lot of the quality control and things like that, or pre-processing, comes from what's done in the traditional system.
Mhm.
But we do try and go away from that when it's things that are related to the model or the DA not being able to handle an observation. So for instance, we still use the visible, or we try to use the visible in DOP, whereas that's not yet assimilated in traditional systems. Also, like we use cloud, the infrared data and things like that, which is not yet exploited in traditional DA. But apart from these like big things which come from needing observation operators and things like that, we base our quality control on what's done for the 4D VAR in our case. So that's that's how we kind of go about it, at least at ECMWF.
Then my next natural line of thought is, once you decide based on your experience with 4D VAR data assimilation that, okay, these are the observations that I can trust, and you also go on experimenting with a new set of observations, and let's imagine this is operational one day, then the point is there will be a dependence on these kind of observation systems. There is a geostationary satellite, but suddenly the calibration is gone wrong, and then the radiances that it measures is different now. Or there is a polar satellite. So, and also there are, depending on the global region, there could be inequalities depending on which government or which set of governments are funding that mission. So how do you see this in that part?
So we have a kind of operational prototype of GraphDOP, and these are all questions that we are currently going through. So we don't have answers for all of them, but it's definitely something that needs to be researched and looked into. An obvious one for us is using dropout so that during training, so that the model doesn't overuse one type of satellite or one specific satellite. We try to make it kind of more make it more equal. Like for instance, we have a GraphDOP model which uses ATMS a lot and not so, it doesn't use like the infrared as much, for instance. And then when we put this in our operational kind of prototype, we see that if we have an ATMS outage, then the predictions become a lot worse, basically, because it was over reliant on this one ATMS instrument. So now we retrain the model. We try to add this dropout so that the model uses ATMS, but is also able to use YASI when ATMS is not available and things like that. So that's one, like for instance, one question. Then we have experiments where we add some bias or we add some random noise to kind of simulate what happens if a satellite becomes decalibrated or things like that. We don't have like all the answers on how everything can be dealt with and if everything can be dealt with in a good enough way for an operational model. But it's things that we are trying to get some answers for, at least.
Thank you. Is there anything different that you think on this, Azadeh, or that Noah is thinking differently?
Not yet. Actually, we are not yet there. So
Yes.
we are
Sure. I get that.
just a few observations. So we are not there yet.
Oh, by the way, I have a question. So how many people on GraphTop are there who work on this parallelly? I'm trying to think about number of people working in ECMWF versus NOAA.
It's almost 8 people, but 5 people are doing the most technical part of the work from the
Okay.
like data processing, generating ZAR files, model development, and evaluation.
Okay.
Officially, we are only maybe 5 or 6 working on it, but we are integrating this code into Anemoy and also making use of all the observation experts that we have in the data assimilation section. So in effect, it spreads across several sections and a lot more people, but on really the core development, we are 5 or 6.
Okay. Maybe we can briefly discuss on how do you ingest the different satellite data. So you can think about it like different modalities. So ERZ is measuring something different of the atmosphere and of the surface, whereas let's say a geostationary satellite measures something different. So how do you bring this information to the neural network for it so that it can process it in time? So how does this thinking goes? Because in a way you can think of them as, yeah, different eyes looking at the same thing.
So in GraphTop, we have different encoders and decoders for each observation type or instrument even. So the model is an encoder processor decoder model with all the encoders being separate for instance, we have an encoder for YASI observations, then we have an encoder for ATMS observations, and then for radiosondes at a specific level or surface observations. Yeah, we have different encoders, different data sets basically for these different observations, and each encoder will receive like 12 hours of this observation type, all the data that fell within this 12-hour window. And then they would get encoded first separately, and then there is a kind of joint encoder which kind of merges all of these different instruments together, and that gets passed to the latent to the processor, so to the latent space. And then the same thing happens when we decode. So first we kind of decode from the latent space onto kind of big joint vector, and then we decode.
We decompose it. Yeah, okay.
Observation types.
I have a very burning question on this, but maybe as a day you would like to say how is it done? Yeah, and what would you say on this?
Yeah, similar to GraphTop, we are using instrument-specific encoders. And what I like to add, for each observation, we ingest both the measured value for that specific observation and the metadata related to that, like location, time, if it's satellite channels, viewing geometry, if it's like radiosonde aircraft pressure level. And so that instrument-specific encoders interpret those different observation types and map them onto a shared spherical latent representation. And then we have, it's a graph structure. So it helps determine which observations can exchange information, largely through their spatial and temporal relationships. And then once they are mapped onto the shared representation, the model can learn how information from different instruments should interact. Exactly similar to what Yulali mentioned.
So let's say on a given time t, there is a radiosonde which has its profile at a given space coordinate xy. Now in time t plus delta t, the radiosonde has moved and it is at some other x plus delta x and at y plus delta y and similar to z. That's fine. You know what I'm thinking is that maybe in a different long time step, it may not be so that the radiosonde is again found at the same location. It will be at a different location. Yeah, how does this complex it is complex in a way, because if you take the whole globe and its representation and you have to feed it. So I was thinking about this called dynamic graph. Is it something that is supposed to take care of this, and what is it?
So the dynamic graphs kind of naturally adapt to the observation to the observations available at any forecast cycle. So we load kind of one 12-hour window of observation at a time. Then we build the dynamic graph. We build the graph for this sample. So the graph nodes will be at the observation locations at that time t, or across that whole 12-hour window. And then for the next window, which we are forecasting, we also have a set of observations from which we also build a graph, which will not have the same nodes as the first one, as the previous one. So that's really the benefits of these like dynamic graphs. Otherwise, you would need to grid your observations to have a fixed graph, which is what we do. We also have a AIFS DOP model, which does exactly that, and it's faster to train, and it's kind of a simpler version of a graph DOP that works very well, but that can't accommodate these moving observations. So we have to grid the observations and actually lose some information.
Very nice. Is it the same in Ocelot, Azadeh?
Yeah, this dynamic graph help the model that the model doesn't require all observations to arrive at the same time or on a regular grid. So if an observation is missing, it's simply not included.
Okay, nice. I need to read more about that because I get the feeling of it, but I don't know the detail. Yeah. Then let's talk a bit about the processor. You kind of encode it in, as we just discussed, from a dynamical graph perspective. So there is node and edges. There's a joint, I would say, distribution space still in the graph, which connects all these instrument or measurement specific encoded information. And then there's the processor. So it could be different, because that's an information that could be processed in time differently. It could be a transformer, it could be a graph also. So what's in the graph DOP? How is it processed in time?
In graph DOP, it's a graph transformer with window detention. So it's kind of window detention that basically goes around the globe, or around the latent space, which is an 096 grid, basically. Yes, so it's a graph transformer. I'm not sure. I think Ocelot may be a bit different.
In Ocelot, we have three types of processor, but the one that we published recently is the hybrid one. We started with end-to-end graph neural networks, so the processor was similar to GraphTAS. It was exactly similar to GraphTAS. But then we switched to hybrid processor, which combines transformer with a spatial graph network. Transformer helps capture temporal relationships and how the atmosphere evolves over time, while graph network propagates information across the spherical mesh and preserve atmospheric spatial structure. So the overall architecture mirrors the problem we are trying to solve. We have heterogeneous observations coming. They are brought together in a shared latent space, and the atmosphere evolves through time. Here is the transformer part, and information moves across the space before we predict the future observations.
And how do you decide that? So of course it could be based on performance, or like efficiency or accuracy. I get that, but is it easy to decide, or is it an engineering problem? That's what I'm trying to ask.
It is a scientific decision, and we cannot claim that this is the best option. We need to compare with different setups to make sure that transformer performs better than end-to-end graph neural network.
In our case for ECMWF, we also benefit a lot from the research and what's done in AIFS, so the operational machine learning forecasting model. And GraphDOP's code is very similar to the AIFS code. It's just kind of adapted to accommodate these dynamic graphs. But for instance, in our case, we didn't try another processor than what's kind of been decided for the operational AIFS.
Okay.
We kind of inherit their trial and errors and their decisions as well. But for AIFS, as they said, it was a scientific decision. They compared different processors, but probably not everything that can be done. It's some decisions that you need to take.
I think Eulalie said it in her answer, like the last answer, that there is this word O96. So I can understand the information is on the whole sphere. That's a spherical mesh. From a graph point of view, I get that. But then where does the O96 comes into the picture? Because how do you define that it is, O96? Or what is it?
So O96 is like a spherical mesh at approximately 100 kilometers, and I think in GraphTop's case, it's as I just said, it's similar to what's done in AIFS. So O96 was a good kind of compromise where you compress enough the information but don't lose too much.
Okay.
Sometimes for like quicker versions and tests, we use an O48 processor. Or you can use more high res like N320 or O256, which is the kind of more high resolution. But again, these are kind of, I think, choices that depends on the resolution that you have as your input data. You need to compress it to be able to decompress it. So you need to be a bit coarser than your input resolution, etc.
Maybe it's a stupid question. So let's say the word is O96. And so does that means there are 96 nodes at this common, at that shared encoded space, the resolution is at 100 kilometer. How?
The O96 is really just the grid name. So
Yes.
so it has an O96 grid has like 40,000 grid points across and it's an octahedral 96 grid. It's just a convention name, I think, from ECMWF. Then how you connect your inputs to each grid point in your processor, so in your latent space, and how many neighbors it has access to, and how you build your graph, that depends on not on the O96 terminology, but just on how you build your graph. So you can either tell the model that one node has access to 3 closest neighbors or to 5 or things like that. If the question is correct.
Yeah. I'm just trying to understand it more clearly because I get this, but I don't know it properly. Do you also convert it to some grids like this, Azadeh, like to this kind of projection where the resolution plays in, like the resolution is there but not explicitly, the resolution factor?
We use the GraphCast style icosahedral mesh, which has 40,000 something nodes.
Yeah, it's I think the same. Maybe it's just a different convention name.
As you just briefly mentioned, Eulalie, that if we have to have faster runs, we can convert it to O48 or something like this. So just thinking about when you have to experiment a lot, quick experimentation results, dirty plots. And of course, but you have to, maintain a sanity check that, okay, it is still following certain standard protocols that I need to preserve during the whole experimentation. So what are the bottlenecks in this kind of big experiments?
So I think in GraphTop, the bottlenecks is really the training time, which is mostly large due to the dynamic graphs generating the dynamic graphs. So that's really a bottleneck that we are as the GraphTop code comes into Anemoy, we have less and less of this problem, but because we benefit from all the developments done in Anemoy, which are very, very nice in terms of efficiency. But that's a big bottleneck. So now we have different ways. Either we do a smaller model where we have a kind of standard set of observations, which we know work well, and we test new data sets like added onto these small models, or we do an O48 version, or we shorten the assimilation window, or we grid observations as well. The training this AIFS top model with gridded observations initially was for debugging purposes. In the end, it happens to be a very good model that performs very, very well, especially in the medium range. But initially, it was a kind of more fast iteration model. Things like that. We have different, but the bottleneck for us, at least, it's more the graph generation.
Okay. And when you started Azadeh on this project, what experiences did you have regarding bottlenecks and faster development cycle?
For us, the bottleneck was entire data pipeline. We had to read massive archives efficiently, build observation to mesh graphs on the fly, handle a huge variation in observation density. We ended up doing a lot of data engineering, rechunking archives using lazy loading and caching, reusing a fixed mesh, and distributing training across GPUs.
Mhm.
Yeah, this was the bottleneck for us, the data itself.
Nice. Mhm. I think we can move slowly towards the verification and diagnostics and trust part of our discussion. And the interesting question is on the truth. You are in the observation domain, and then if you have to, do a verification at a certain grid point, what's the truth for you?
So during training, the truth for us is observations. So, and I think for Ocelot, it's the same. So then when we verify our forecasts, we tend to verify against observations, ideally against independent observations that weren't used for training.
For example?
Like a set of surface stations that weren't used in the training or things like that.
Okay.
Then we always get this question of we should verify against analysis. That's a big debate.
Yeah.
We are not using like reanalysis or analysis, so at short lead times we will be further away from the analysis than IFS would be, especially in like remote areas where there are no observations, because the analysis then doesn't get if there's no observations to update the analysis, then the analysis stays the same, and then the forecast is very close to the analysis in shorter lead times. After a few days, this effect kind of dies down, but yeah, it's an ongoing kind of question. We tend to verify against observations, or if we are to do analysis-based verifications, then we try to use independent analysis for instance, using the UK Met Office analysis to verify both IFS and GraphTop, which is a fairer comparison than verifying against the IFS analysis, for instance.
Okay. Sounds fair. Azadeh, what's your take on this? Or is it, yeah.
I agree with you, Lily, and just I like to add, because when we use analysis, they are also trying the assumption of data assimilation and numerical weather prediction system. It is another reason we first evaluate based on the observation itself and use analysis just as a reference, not absolute truth.
Now let's come to the interesting, like a bit more interesting part of this. When we started this discussion, that we want to check whether from observation itself the model can learn the dynamics of the atmosphere. And I think both of the works have stressed on this quite a lot in some part of the journey. I mean, how do you, basically check that the model has learned something dynamical?
I think verifying like medium range forecasts is a good way of doing that, because at very short term, like a 12-hour forecast or something, you may, if you're verifying against an observation, maybe you think that your model is doing very well, but maybe it has overfitted to a specific station location or things like that. But to have a good forecast at a station location 10 days ahead, at least in any kind of physical model, you would say that that's not possible unless the model has learned the dynamics of the atmosphere. because 10 days ahead, it's not like we don't train our model to forecast 10 days ahead. So if it got a forecast correctly 10 days ahead, it means that it has this dynamics of the atmosphere to be able to forecast at this observation location 10 days ahead. So I think that's a good way. Or we can also maybe track, for instance, tropical cyclones and things like that, which help to have a more visual kind of check that model is learning atmospheric dynamics.
Azadeh, would you like to add something to this?
We need to look beyond one average error score. We should ask, do the errors grow in a reasonable way with forecasted time? Do different instruments tell a consistent story? Does the model still perform well across different seasons, regions, and weather situations? And we can also remove certain instruments or channels on purpose and see how the model responds.
Maybe like a side question to this. So let's say, your 5-member team have worked hard to get the output up and running, and you can get a medium range forecast. Now these are like good questions which you want to confirm that if it is there, that's very good. I mean, ultimately, as you said, that the model has not learned the dynamical aspects because you have not trained for a 10-day forecast. It's just 12, then 12 is given for the next 12. So then do you give your results to other member of like the whole NOAA or ECMWF so that they can check these things, or is it still 5 to 6 people who are looking into these aspects?
For us, when it is purely a research model, or for which we have scores for like 2022 or 2023, then it's mostly still us 5 doing it. But now that we have this kind of operational prototype that runs daily and that has gives forecasts daily, then now these forecasts are being given to the analysts, or to being like they are archived and available to all, because we can't look at everything, and also people have different expertise in different weather situations or things like that, which we are very happy to get their view and their insight on, to develop then the next kind of version, etc.
Cool. I think one other aspect is that the model may learn a very good correlation with all the multivariables that are present. And also there are ways in which you can actually, with respect to backpropagation, you can see where the activation spaces are, or what is leading to that particular result. What I mean is that which part of the whole family of observation is more responsible for a certain output at a given region. Has it ever happened in your experience that you expected, like, for example, including EASI, there should be something on there, like you expect something because you included that instrument, but then it didn't work in that way. During development phase or even till now, did you see something like this, or did you face something like this?
In general, we see quite consistent messages with what's seen in 4D VAR. So, for instance, the microwave is more impactful than the infrared, things like that. But when we implemented FSOI and things like that, we do see some odd things, such as one channel in YASI being used very much and the others much less. We think it's probably because this channel is is easier to use, and then it will kind of add or a bias to the other ones, or something like that. We think maybe that's and that was something a bit odd. But apart from that, generally we see things which are quite similar to 4D VAR. The only thing is also we see that the way you present the observations to the model is very important and can have a big effect. For instance, at first we were using a single data set for radiosondes. So we were having we had a pressure level column and then a TUV column. And that gave much worse results than when we split this radiosonde data set into per level data sets. So this is something that we wouldn't have necessarily thought of, but having instead one radios on data set for 500, 500 one for 850, for instance, this seemed to work a lot better in the model. So it's the kind of these things by which we are sometimes a bit surprised more than the impact of the actual patient types.
Wow, I mean, I never thought that, I mean, it could happen like this, but yeah. Azadeh, did you face something like this that you expected and then, or as Eulalie mentioned?
Yeah, we are also implementing FSOI for sensitivity diagnostics. And yeah, we are seeing that. And what concerns me is when we, remove from a specific observation, we see unstable changes in the forecast. This is what I'm currently looking into.
Okay. What's the loss function then? Is it MSE or is it something different in your standard routine training?
We have started with Huber loss, but now it is MSE. It's the weighted, but we are using equal weight right now. But the future plan is, using FSOI output to reassign weights in the loss function.
Huh. Are you also trying to do something like, you give more weights to near the boundary layer and then above the like in the free tropospheric region, there are less, weights assigned. Is it something also part of this whole design pipeline?
Not yet, but we are going to look into that. As I said, based on the FSOI, when we implement FSOI, we see the impact of each observation at different pressure levels.
Okay.
And based on the target that we evaluate, it can be radios on a different levels or aircraft at different levels. So, and based on that, we can, not training from scratch, we can fine tune that based on the new results from the FSOI and see how it impacts the forecast.
Okay. What about graph top ensemble or a graph top cast? I don't know how would you put it, but or ocelot cast. So is it something that you people foresee in the coming years?
Yes, I think it's really important because the MSE loss tends to smooth things, especially in observations, maybe even more. So we currently don't do it, but we should have most things in place to do CRPS training as it's done for AIFS ensemble. We're first trying to kind of have a mature version of the deterministic model, which is faster to train, faster to evaluate, etc. And then we will move on to probabilistic versions. But so it's we expect that to come, but not just yet.
Okay. Okay, and what about what's NOAA's? Is it in the next I don't know 4 or 5 years?
Yeah, of course. But before that, we need to increase the forecast lead time, increase the capacity of the model. We have other
yes.
So I reassigning the weights and make sure that this is the final, deterministic forecast for us, and then we can move. Of course, we can move to ensemble forecast.
Okay. I guess we can move to the integration with operations part of the discussion. In the beginning years, as Eulalie mentioned, that it is within the research team, but as the results become more and more accurate, the results could be distributed to different sections and feedbacks could be received. What's the natural pathway? So, okay, at some point there's a group leader who says, okay, now this could be integrated, or is it like I don't know, at what stage does it move from pure research experiment to, more into the operational side of seriousness?
So I think to us it was more when, as the model got more and more kind of mature, and when we got a better feeling that this could really be a future operational system. And what we're trying to do now at ECNWF is try to have a smooth kind of forecast research to operation mode. So kind of do things together. When we implemented this operational prototype, we do it together with the operation side that process the observations. They are very much included into the way that they like in the way of processing the observations for a graph top like system. So they did most of the work for this part, which then we can integrate into a research suite. For now, this prototype is running as a research suite, but we coded things in a way that could hopefully be moved to operations not so difficultly. So yes, but yeah, ultimately the decision will come from above, of course, of how what ECMWF wants to go forward with.
And Azadeh, would you like to add something?
Yeah, for us, research to operations has to be a joint effort from the beginning. We cannot develop the model in isolation and then simply hand it over to an operational team. Data teams need to manage format, latency, calibration, outages, and we have satellite data simulation experts that help us understand biases, observation errors, channel behaviors. Verification team define their fair evaluations. We have model developers work on architecture, and we should work together.
But my question here is, which of the teams are more difficult to handle with? If you have, if you are working on this kind of a pipeline, observation end to end, which of the other teams are more difficult to handle? Like, well, yeah, it's a fair and simple question, because some teams can, have very strict rules or strict guidelines about how to, whether this could be taken in, this could be handed over from you to them. So I was just thinking, which of the divisions have their more strict criteria? Yeah.
I feel like it should be verification teams.
Okay.
To have these fair evaluations.
Okay.
Because it's different model, different goal, and different verification.
Okay.
So, yeah, this is my opinion.
No, fair enough. Yeah, maybe it's a very, I would say, futuristic question, but still it's a question which a lot of people think that these end-to-end, whether do we need the classical DA, or, this part is always there. That because if it is observation end-to-end, then of course, I'm not saying that NWP is not needed or the whole separate parallel pipeline. The research in that direction should also continue. But where do we see kind of how the roles will change? Because right now, even in current AIFS, or the analysis state is very much important. But then in next 2-3 years, we will have an end-to-end, I hope so, an end-to-end running operational suite. Then, yeah, how will the role change? Have you thought about it?
It's a difficult question. At least at ECMWF, there's no plans, of course, to stop any development on 4D VAR or on the IFS. I think it's important to keep both. The motivation to building this end-to-end system is not to replace 4D VAR or the physical model. It's to have something which is independent, that can run independently. It has its advantages, but also its disadvantages. So I think people will need to adapt. So observation experts, people will need to adapt to how to best use their observation types in 4D VAR and how to best use it in an end-to-end system. Not in one or the other. I think that's what I see as the adaptation that will be needed. But yeah, in the coming years, I think there is no risk for either or.
Yeah. Would you like to add anything, Azadeh, on this?
I completely agree with you, Lottie, because we are not there yet, and I think we see the most realistic role as a parallel experiment system rather than replacement for data assimilation for the next couple of years.
Okay, thank you. Maybe so we are slowly moving to our closing part, and the question that I have is that, like, what should people watch out? What is coming next for Ocelot, and what is coming next from GraphTOP? Would you like to share something on this?
I think for GraphTop, it's hopefully something, maybe a blog post or something like this on this real-time prototype that we have and all the challenges that we have to face to put such a system into operations. Yeah, we also have these AIFS-DOP and AIFS-DOP pre-analysis papers that just came out and that hopefully will be submitted to a peer review paper, which people can watch out for that as well. Yes, I would say, and of course for people interested, the integration of GraphTop and of dynamic graphs, etc., into Anemoy, which should come by the end of this year, hopefully, so people can then play around.
Okay. Cool. And for Ocelot, what would you say, Azadeh?
Yeah, we are working on increasing the forecast lead time and also the model capacity and different architecture. And we posted our first preprint and archive, and which is also submitted on AIES. And also we are going to work more on control tests, like evaluation on different seasons, regions, and weather conditions.
Yeah, thank you very much for sharing your opinion. I guess we have come to an end for this discussion on this podcast. Yeah, this also brings us to the closure of our course too, and I hope people listening to this have enjoyed the discussion. Thank you. Thank you both.
Thank you.